For as long as humans have gazed at the stars, we have asked the most profound questions. What is the universe made of? Why does it behave the way it does? Is there a deeper, hidden structure beneath everything we see? These questions have shaped the course of human thought, leading to remarkable discoveries and ever more intricate theories about the nature of existence. At first, we believed the world was composed of basic elements: earth, water, air, and fire. Then came the idea of atoms, tiny building blocks that formed everything around us. As science progressed, we discovered that even atoms were not indivisible. They contained smaller parts: protons, neutrons, and electrons. But our search did not stop there. We found that protons and neutrons were themselves made of even tinier particles called quarks. Each time we thought we had reached the most fundamental layer of reality, another, deeper level appeared. Now we find ourselves facing an even more extraordinary possibility. What if, at the deepest level, everything in the universe is not made of individual particles, but of something else entirely? What if all matter, all forces, and even space and time itself arise from the vibrations of unimaginably tiny invisible strings? This is the idea behind string theory, one of the most revolutionary concepts in modern physics. It suggests that the universe is not just a collection of point-like particles, but a vast, intricate symphony, where each particle is a note played by a vibrating string. Just as a violin string can produce different musical tones depending on how it vibrates, these fundamental strings give rise to everything in existence: electrons, quarks, light, gravity, and even the forces that hold the universe together. If string theory is correct, it could be the long-sought unifying theory of physics, bringing together everything we know about the universe into one grand framework. It could bridge the gap between Einstein's theory of relativity, which explains the vast cosmos, and quantum mechanics, which governs the microscopic world. It could explain the true nature of black holes, the beginning of the universe, and the hidden dimensions that may exist beyond our perception. But string theory is not just another step in science. It is a radical shift in the way we understand reality. It challenges our deepest assumptions and takes us into a world far stranger than we ever imagined. This documentary is a journey into that world. We will begin at the very start, the great mysteries of physics that led scientists to seek a deeper theory. We will explore the strange and beautiful mathematics behind vibrating strings and extra dimensions. We will see how string theory might hold the key to understanding the very fabric of the cosmos. The road ahead is long, and the ideas we'll encounter are profound. But we will proceed slowly, step by step, allowing time to absorb each concept fully. Chapter 1: The Quest for the Ultimate Theory. For thousands of years, humanity has searched for order in the universe. Beneath the ever-changing chaos of nature, we have always sensed something deeper, a hidden structure, a pattern, a set of rules that governs everything. From the motion of planets to the rise and fall of tides, from the behavior of tiny particles to the vastness of galaxies, we have sought to understand the forces that shape reality itself. This search has led us through many stages of discovery. The ancient Greeks pondered the nature of matter, proposing that all things were made of indivisible particles called atoms. Centuries later, Newton formulated his laws of motion and gravity, showing that the same force that pulls an apple to the ground also keeps the moon in orbit around the Earth. Then came Maxwell's equations, revealing that electricity, magnetism, and light were all part of a single unified force. And then in the early 20th century, everything changed. Two revolutionary ideas emerged: quantum mechanics and Einstein's theory of relativity. Each transformed our understanding of the universe in ways no one had imagined. Quantum mechanics uncovered the bizarre, unpredictable behavior of particles at the smallest scales, where objects could be in multiple places at once, and reality itself seemed governed by probabilities rather than certainties. Meanwhile, relativity rewrote the rules of space and time, showing that gravity was not really a force, but a curvature in the fabric of space-time caused by the presence of mass. These two theories are the cornerstones of modern physics. They explain everything we see, from the smallest atoms to the largest galaxies. They have been tested in countless experiments and have never failed. And yet, they do not fit together. This is the great paradox of modern science. Quantum mechanics governs the microscopic world, and general relativity governs the cosmic realm. But when we try to combine them, the equations break down. The numbers explode into infinities. The laws that work so perfectly on their own become meaningless when placed side by side. This contradiction suggests that something fundamental is missing, a deeper theory, one that can unite the forces of nature into a single harmonious framework. This is the dream of physicists. The search for such a theory has been long and difficult. Scientists have tried many approaches, testing new ideas and discarding those that failed. Decades passed, and while progress was made, no theory could fully bridge the gap between quantum mechanics and relativity. Then, in the late 20th century, an extraordinary idea emerged. It suggested that everything we thought we knew about the universe was incomplete. It proposed that the fundamental building blocks of reality were not tiny, point-like particles, but something much more exotic, something smaller than anything we had ever imagined, something vibrating, something string-like. String theory was unlike anything that had come before. It was not just another attempt to solve a problem, it was a complete reimagining of the universe. It suggested that all particles, electrons, quarks, photons, even the mysterious force of gravity, were not separate things, but different vibrations of the same underlying entity, an incredibly small, one-dimensional string. Just as the different notes on a violin string arise from different ways the string vibrates, the different particles of nature arose from the various ways these fundamental strings could move. At first, this idea seemed too strange to be true, but as physicists explored its implications, something astonishing happened. The theory predicted the existence of a particle that had never before been successfully included in quantum mechanics: the graviton, the carrier of gravity itself. This meant that string theory naturally included gravity, something no other quantum theory had been able to do. For the first time, a single framework existed that could unite all the forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Everything fit together in a way that had never been possible before. But there was a price to pay. String theory required extra dimensions. In our everyday experience, we perceive the universe as having 3 dimensions of space: length, width, and height, and 1 dimension of time. This 4-dimensional reality is the foundation of both classical physics and Einstein's relativity. But string theory demanded something more. The equations only worked if the universe had additional dimensions, perhaps 10 or even 11 in total. These extra dimensions, scientists proposed, were hidden from view, curled up so tightly that they were invisible to us, just as a tiny thread might appear one-dimensional from a distance, but reveal additional structure upon closer inspection. This idea was breathtaking and unsettling. If true, it meant that the universe was far more complex than we ever imagined. It meant that there were hidden layers of reality we had never seen. It meant that our familiar world was just a tiny part of a much larger, more intricate cosmic structure. And yet, despite its beauty, string theory remained unproven. The fundamental strings were so small, far smaller than even the tiniest subatomic particles, that no experiment could directly detect them. The extra dimensions were so compact that they, too, remained beyond our ability to observe. For all its mathematical elegance, string theory faced a great challenge. How could it be tested? How could we ever know if it was truly the answer to the great puzzle of the universe? The journey to answer these questions would take physicists deeper into the mysteries of black holes, deeper into the origins of the cosmos, and deeper into the very structure of space and time itself. And so the quest continued. A quest for the ultimate theory, a quest to uncover the fundamental truth of existence, a quest that perhaps was only just beginning. Chapter 2: The Building Blocks of Reality. To understand string theory, we must first understand what it is trying to replace. For centuries, humanity has tried to break down reality into its smallest, most fundamental pieces. We have asked, what is everything made of? If we keep dividing matter into smaller and smaller pieces, will we eventually reach a final, indivisible unit? Something so basic that it cannot be broken down any further. The ancient Greeks wrestled with this question over 2,000 years ago. Some believed that matter was continuous, that it could be divided endlessly. Others, like the philosopher Democritus, had a different idea. He imagined that all things were made of tiny, indivisible units that could not be broken apart. He called these fundamental pieces atoms, which in Greek means uncuttable. For centuries, this idea remained nothing more than a theory. There was no way to prove it, no way to see these supposed building blocks of reality. But as science progressed, experiments in chemistry and physics started to reveal a hidden order in nature. Different substances could combine in precise ways to form new materials, and these combinations always followed specific ratios, as if matter were built from a collection of tiny, discrete pieces. This was one of the first clues that Democritus might have been right. By the early 20th century, scientists had confirmed it. Atoms were real. But the discovery did not end there. As scientists probed deeper, they found that atoms were not the most fundamental entities after all. Instead of being solid, indivisible objects, atoms had structure. Each atom contained a central nucleus, made up of protons and neutrons, and this nucleus was surrounded by electrons moving in orbits. The discovery of the atomic nucleus was groundbreaking. It showed that even the uncuttable atom could, in fact, be divided into smaller parts. But the surprises did not stop there. Over the next few decades, scientists discovered that even protons and neutrons were not fundamental. They were made of even smaller particles called quarks. Unlike protons and neutrons, quarks could never exist alone. They were always tightly bound together, held in place by a powerful force known as the strong nuclear force. At this point, scientists had uncovered a deep and hidden structure in nature. The universe, they realized, was not built from just one type of fundamental entity. Instead, it was made of a family of elementary particles, each playing a different role in the cosmic dance of existence. These particles could be categorized into two main groups. The first group consisted of matter particles, the fundamental building blocks that make up everything in the universe, from the tiniest grains of sand to the largest galaxies. These particles were divided into two major categories: quarks and leptons. Quarks are the fundamental building blocks of matter, serving as the building units of protons and neutrons, which, in turn, form the atomic nucleus. However, quarks are never found alone in nature. They always exist in groups due to the powerful force that binds them together, known as the strong nuclear force. This force is mediated by particles called gluons, which act as an invisible glue, ensuring quarks remain confined within larger structures. The concept of quark flavors. Quarks exist in 6 different types, commonly referred to as flavors. The term flavor in physics is simply a way to distinguish between different kinds of quarks based on their intrinsic properties. The 6 flavors of quarks are up, down, charm, strange, top, and bottom. Among these 6, the up and down quarks are the lightest and most stable. They are the primary components of protons and neutrons, which are the fundamental constituents of atomic nuclei. These 2 quarks are responsible for forming the matter that makes up the observable universe, including stars, planets, and living beings. The other 4 quarks, known as charm, strange, top, and bottom, are significantly heavier and highly unstable. These quarks do not exist in ordinary matter and can only be created in high-energy environments, such as particle accelerators or during extreme cosmic events like supernova explosions. Due to their large mass, these quarks decay almost instantly into lighter particles, preventing them from contributing to the stable structures found in the universe. Formation of protons and neutrons. Quarks combine in very specific ways to form larger composite particles known as hadrons. These hadrons are divided into 2 main categories: baryons and mesons. Baryons are composed of 3 quarks. The most well-known baryons are protons and neutrons, which are essential for the formation of atomic nuclei. A proton consists of 2 up quarks and 1 down quark, while a neutron consists of 1 up quark and 2 down quarks. The combination of these quarks within protons and neutrons determines the overall charge and stability of atomic nuclei. Mesons, on the other hand, are made up of 1 quark and 1 antiquark. Unlike baryons, mesons are highly unstable and exist only for brief moments before decaying into other particles. They are often produced in high-energy environments, such as during cosmic ray interactions or inside particle accelerators. The mystery of quark confinement. One of the most intriguing aspects of quarks is that they never exist alone in nature. This phenomenon is due to the unique behavior of the strong nuclear force, which governs their interactions. Unlike other fundamental forces such as gravity or electromagnetism, which become weaker as objects move apart, the strong force behaves in the opposite manner. It becomes stronger as quarks attempt to separate. This peculiar property ensures that quarks always remain bound together, a concept known as quark confinement. If enough energy is applied in an attempt to separate quarks, rather than isolating them, the energy instead leads to the creation of new quark-antiquark pairs. This means that no experiment has ever succeeded in observing a free quark. Instead, whenever scientists try to pull quarks apart, the energy supplied is immediately converted into the formation of additional particles, maintaining the rule that quarks must always exist within groups. The role of heavy quarks in high-energy physics. Although the heavier quarks such as charm, strange, top and bottom do not play a role in forming everyday matter, they are of great interest in the field of particle physics. Scientists study these quarks in advanced research facilities like the Large Hadron Collider, where they can be produced in high-energy collisions. The study of these quarks provides valuable insights into the fundamental nature of the universe, including the forces that govern particle interactions and the conditions that existed in the early moments after the Big Bang. In summary, quarks are the most fundamental components of matter, existing in 6 different flavors. Among them, only the up and down quarks are responsible for forming the stable matter that surrounds us. The heavier quarks, while unstable and short-lived, play a crucial role in scientific research, helping physicists explore the fundamental forces of the universe. Bound together by the strong nuclear force, quarks form the protons and neutrons that serve as the building blocks of all known matter, ensuring the stability and structure of the universe as we know it. Now, let's talk about leptons. Leptons are a special group of fundamental particles that, unlike quarks, do not need to combine with other particles to exist. They can move freely through space without being bound by the strong nuclear force. The most well-known lepton is the electron, a tiny negatively charged particle that orbits the nucleus of an atom. Electrons play a crucial role in forming atoms, enabling chemical reactions and generating electricity. Without electrons, atoms could not bond together to create molecules, and life as we know it would not be possible. However, electrons are not the only leptons. They have 2 heavier and less stable relatives, the muon and the tau. These particles behave similarly to electrons but are much more massive. Because of their larger mass, they are highly unstable and exist for only a fraction of a second before quickly decaying into lighter particles, usually electrons or neutrinos. While they do not play a role in everyday matter, their existence helps scientists understand the fundamental nature of particles and forces in the universe. In addition to these charged leptons, there is another group known as neutrinos. Neutrinos are incredibly light, neutral particles that barely interact with anything. They are sometimes called ghost particles because they can pass through solid objects, even entire planets, without being stopped. This is because neutrinos do not feel the electromagnetic force like electrons do, nor do they experience the strong nuclear force like quarks. Instead, they interact only through the weak nuclear force, making them extremely difficult to detect. Despite their ghostly nature, neutrinos play a crucial role in the universe. They are produced in enormous numbers during nuclear reactions, such as those occurring inside the Sun. In fact, trillions of neutrinos pass through your body every second without you even noticing. Scientists study neutrinos to learn more about the processes that power stars, supernovae, and even the formation of the universe itself. In summary, leptons are a unique type of fundamental particle that do not need to bond with others to exist. Electrons, the most familiar leptons, are essential for atoms, chemistry, and electricity. Muons and tau particles are their heavier, short-lived cousins, appearing only in high-energy environments. Neutrinos, on the other hand, are nearly invisible particles that play a key role in nuclear reactions, helping power the Sun and shaping the universe in ways we are still trying to understand. Now that we have talked about the first group, matter particles, quarks and leptons, let's move on to the second group of particles. The second group of particles was composed of the force carriers, the particles responsible for transmitting the fundamental forces of nature that governed all interactions in the universe. These particles acted as messengers, transferring energy and influence between matter particles. One of the most familiar force carriers was the photon, the particle responsible for electromagnetic interactions. Photons were not only the fundamental particles of light, but also carried the force that governed electricity, magnetism, and all interactions between charged particles. Every time an electron moved through a wire or a magnet attracted a piece of metal, photons were at work behind the scenes. Another crucial force carrier was the gluon, the particle responsible for the strong nuclear force. The strong force was what held quarks together inside protons and neutrons, preventing them from flying apart despite their immense energy. Without gluons, protons and neutrons could not exist, and atoms themselves would never have formed. The strong force was so powerful that it was responsible for more than 99% of the mass of ordinary matter, as most of the weight of a proton came from the energy of the gluons binding the quarks together rather than the quarks themselves. Then there were the W and Z bosons, the force carriers of the weak nuclear force, which governed radioactive decay and nuclear reactions. Unlike gluons and photons, which were massless, the W and Z bosons were incredibly massive, making the weak force much weaker than electromagnetism or the strong nuclear force. Despite its name, the weak force was crucial for processes like beta decay, which transformed neutrons into protons inside atomic nuclei. Without this force, the nuclear reactions that powered stars, including the fusion reactions that allowed the Sun to shine, would not take place. These two groups, matter particles and force carriers, formed the foundation of the Standard Model of particle physics, the framework that described all known particles and their interactions, except for gravity. This model had successfully explained almost every observed phenomenon in particle physics. But there was a problem. The Standard Model left out one of the most important forces in the universe, gravity. Gravity, as described by Einstein's general theory of relativity, was not like the other forces. In the Standard Model, forces were described as the exchange of force-carrying particles. The electromagnetic force was carried by photons. The strong nuclear force was carried by gluons. But gravity? The Standard Model had no place for it. Physicists suspected that if gravity worked like the other forces, it should have its own force-carrying particle, a particle that would mediate gravitational interactions, just as photons mediated electromagnetic interactions. They called this hypothetical particle the graviton. But there was a problem. Gravity did not behave like the other forces. While quantum mechanics described reality in terms of probabilities and wave-like behaviors, gravity, as Einstein described it, was something entirely different. It was not a force in the way electromagnetism or the nuclear forces were. Instead, gravity was the result of the curvature of space-time, the very fabric of reality itself. Massive objects like planets and stars bent space-time, and this curvature created what we experienced as gravitational attraction. When physicists tried to fit gravity into the quantum framework, something went terribly wrong. The equations broke down. The calculations produced nonsensical infinities. numbers that were so large that they had no physical meaning. This was a sign that something was deeply wrong, that there was a missing piece to the puzzle of reality. And so physicists faced a mystery. On one hand, they had quantum mechanics, which explained the behavior of the tiniest particles with unmatched precision. On the other hand, they had general relativity, which described the force of gravity and the bending of space and time on a cosmic scale. Each of these theories worked beautifully on their own. But when they were brought together, they refused to cooperate. This was the great contradiction of modern physics. And this was where string theory entered the picture. Instead of treating particles as tiny, indivisible points, string theory proposed something radically different. It suggested that all of the elementary particles we knew, the quarks, electrons, photons, and even the graviton, were not actually fundamental. Instead, they were different vibrations of the same underlying entity, an entity so small that we had never been able to see it. A string, a tiny one-dimensional loop of energy, vibrating in multiple ways, giving rise to the entire universe. Imagine a violin string. When plucked, the string vibrates in different ways, producing different musical notes. In the same way, the strings of string theory vibrate in different ways, and each vibration corresponds to a different particle. One vibration produces an electron, another produces a photon, another produces a quark, and one very special vibration produces the graviton, the particle responsible for gravity. This was the breakthrough that physicists had been searching for. String theory did not just add gravity to quantum mechanics. It made gravity a natural part of the framework. It did something no other theory had been able to do. It united quantum mechanics and relativity. But there was a cost. String theory only worked if the universe had extra hidden dimensions, dimensions beyond the three we see in everyday life. These extra dimensions, according to string theory, were not visible because they were curled up in tiny hidden shapes, too small for us to detect. This idea was shocking. It suggested that the world we knew was just a small part of a much larger, more complex reality. It meant that space was not just three-dimensional, as we had always assumed, but had additional layers folded into it. Layers that shaped the universe in ways we could not yet fully comprehend. And so the search for a final theory, the theory of everything, took a dramatic new turn. If string theory was right, then the fundamental nature of reality was not based on particles, but on vibrations. Not on points, but on loops. Not on matter, but on music. A cosmic symphony played out on the smallest scales of existence. But if string theory was the answer, then why had we not yet seen any evidence of it? Why had we not found these extra dimensions? And if strings were real, then what were they made of? These questions would take us even deeper into the hidden fabric of the universe itself. And so our journey continues. Chapter 3. The Nature of Strings Beyond the Visible Universe. In the search for a deeper understanding of the cosmos, we must look beyond the conventional building blocks of matter. In classical physics, particles are often treated as the most basic, indivisible units of nature. Yet in the world of string theory, particles are not elementary. They are, in fact, complex manifestations of tiny, vibrating strings. These strings represent a completely different concept of the universe, one where every particle, every force, and even the fabric of space-time itself arises from the vibrations of these incredibly minute strings. But how do these strings work, and why are they so important to our understanding of reality? To understand string theory, we must start with a simple yet profound idea: the concept that everything is made of vibrating strings. Each string, while infinitesimally small, behaves in a very specific way, and the way these strings vibrate gives rise to the particles that make up everything we observe. While this idea might sound abstract at first, it carries immense implications for how we view the universe and its fundamental workings. Strings as fundamental building blocks. At the most basic level, a string is not like a piece of string you might see on a spool. These strings are one-dimensional. They are not little dots or points, but rather extended objects, almost like tiny threads or filaments with no thickness. These strings are much smaller than atoms or even subatomic particles. To put their size into perspective, they are about 1/1,000,000,000 of a trillionth of a centimeter, far smaller than anything we can directly observe with current technology. What makes this concept so remarkable is that these tiny strings, which you cannot see or touch, are the fundamental building blocks of all matter and energy. The particles we are familiar with, such as electrons, photons, and quarks, are not point-like objects, but rather vibrational modes of these strings. In this view, instead of thinking of the universe as a collection of separate particles, string theory suggests that everything is connected through a single underlying entity, the string. Now, how does this work? In the traditional view of particles, each particle is considered a discrete point with its own properties, like mass, charge, and spin. But in string theory, these properties emerge as a result of the way the string vibrates. Much like a guitar string can vibrate in different ways to produce different notes, a string in string theory can vibrate in different patterns, giving rise to different particles. Imagine for a moment that you're holding a rubber band between your fingers. You can pluck it, stretch it, and cause it to vibrate in different ways. Each of these vibrations would create different movements, producing a different result. Similarly, a string in string theory can vibrate in a multitude of ways, each corresponding to a specific type of particle in the universe. Some vibrations might create a photon, the particle of light, while others might generate an electron, a quark, or even a force-carrying particle like the graviton, responsible for the force of gravity. The vibrations and frequencies of strings. Now that we know that strings vibrate to create particles, the next question is, what controls the vibrations of these strings? The answer lies in the tension and energy inherent to the strings. Just like the tension in a guitar string determines the frequency of the notes it produces, the tension in a string determines its vibrational frequency. In string theory, this tension is incredibly high, which is why strings are so small. They would be impossible to observe if they were any larger. The frequency of a string's vibration determines what kind of particle it will represent. In quantum mechanics, each vibration of a string corresponds to a specific energy level. And energy, as we know from Einstein's famous equation, is related to mass. Thus, a higher frequency vibration of a string could correspond to a heavier particle, while a lower frequency vibration might correspond to a lighter one. This means that the properties of all particles, whether they have mass or charge, are determined by the string's vibrational frequency. For example, an electron is the result of a string vibrating at a certain frequency, while a photon corresponds to a string vibrating at a different frequency. But what makes string theory so powerful is that it doesn't require us to treat each particle as an entirely separate entity. Instead, all the particles in the universe are just different vibrational modes of the same fundamental string. String theory and the forces of nature. One of the most compelling aspects of string theory is that it doesn't just explain particles, it also explains the forces that govern their behavior. In our traditional view of physics, we have four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces operates on different scales and in different contexts. But string theory offers a more elegant and unified explanation. According to string theory, each of these forces is associated with a different type of vibration of the strings. In particular, the force of gravity, which has long been difficult to explain in quantum mechanical terms, emerges naturally from the vibrations of strings. The graviton, the hypothetical particle that carries the force of gravity, is simply a particular vibration mode of a string. Electromagnetic forces, which govern how charged particles interact, are described by the exchange of photons, another type of vibration. The weak nuclear force, responsible for processes like radioactive decay, and the strong nuclear force, which holds the nuclei of atoms together, can also be explained by the vibrations of strings. This idea of unifying all the forces of nature through string theory is incredibly powerful. It suggests that, at the deepest level, everything in the universe, whether it's a fundamental particle or a force, can be understood as a manifestation of different vibrational modes of a single underlying entity, the string. Extra dimensions, the hidden realities. One of the most striking and mysterious aspects of string theory is its prediction of extra dimensions. We are familiar with 3 spatial dimensions, length, width, and height, as well as 1 dimension of time. But string theory suggests that there are additional spatial dimensions that we cannot observe directly. Why would string theory require extra dimensions? String theory requires more than 3 dimensions, primarily because the behavior of strings, how they vibrate and interact, depends on the geometry of the space they exist in. The underlying reason for needing extra dimensions stems from the mathematical structure of string theory, which relies on specific properties that only work in higher dimensional spaces. Here's a detailed breakdown of why more than 3 dimensions are necessary. 1. Vibrational modes and consistency. In string theory, particles are modeled as tiny strings that can vibrate in different ways. The variety of particles we observe, like electrons, photons, and quarks, are different vibrational states of these strings. In 3-dimensional space, the string has very limited ways to vibrate. However, for string theory to account for the broad range of particles and forces observed in nature, the string must be able to vibrate in many different patterns. To allow for this variety, additional dimensions are required. In higher dimensions, such as 10 or 11, there are more possible directions for a string to oscillate, giving rise to more potential vibrational modes. These vibrational modes correspond to different particles. Without more than 3 dimensions, string theory simply cannot accommodate the complexity needed to explain all the forces and particles in nature. 2. Mathematical anomalies. When string theory is formulated in just 3 spatial dimensions, the equations that describe the strings and their interactions become mathematically inconsistent. For example, certain symmetries and mathematical properties that are fundamental to string theory break down in 3 dimensions. In the case of quantum consistency, string theory requires a higher number of dimensions to avoid problems like anomalies, mathematical inconsistencies that can lead to contradictions. For the theory to work without these inconsistencies, it turns out that 10 dimensions, 9 spatial and 1 temporal, are necessary. This higher dimensional space allows the equations to remain consistent and free from mathematical errors. Number 3. Unification of forces. One of the main goals of string theory is to unify all the fundamental forces, gravity, electromagnetism, and the nuclear forces, into a single framework. To achieve this, string theory needs to describe how forces like gravity, which operates on large scales, and electromagnetism, which governs the behavior of particles on small scales, work together. In 3 dimensions, it's difficult, if not impossible, to reconcile these forces in a unified theory. The extra dimensions allow for a more unified interaction between these forces. By using higher dimensional spaces, string theory provides the framework needed to describe gravity, electromagnetism, and quantum mechanics in a consistent way. 4. Compactification. The extra dimensions in string theory don't need to be large and observable. In fact, they're thought to be compactified, meaning they are curled up into very tiny spaces, much smaller than atoms, and are not detectable by current instruments. Why compactify? Because the theory requires these extra dimensions to exist mathematically, but we do not observe them in everyday life. The compactification of dimensions allows string theory to maintain the benefits of higher dimensions while ensuring that our observable universe remains 3-dimensional in scale. The extra dimensions exist on extremely small scales and do not interfere with our familiar 3D world. 5. Mathematical structure of string theory. String theory is fundamentally rooted in higher dimensional geometry. To make sense of the vibrational properties of strings, the theory relies on sophisticated mathematical objects like Calabi-Yau manifolds, which are complex geometric shapes that exist in the extra dimensions. These manifolds describe how the extra dimensions are compactified, and their shape determines the types of particles and forces we observe. Without these extra dimensions, the geometry necessary for the theory to describe particles, forces, and interactions would not exist, leaving string theory unable to describe the universe in the way we observe it. Chapter 4: The Dynamics of String Interactions, Forces, Gravity, and the Birth of a Unified Theory. In the vast expanse of string theory, understanding how strings interact with one another opens a deeper door to unraveling the mysteries of the universe. Just as an orchestra creates harmonious music from the unique interactions of individual instruments, the strings in string theory work together in complex patterns, shaping the forces and particles that comprise the very fabric of reality. In this chapter, we explore how these interactions go beyond mere particle creation and examine how they shape the fundamental forces of nature: gravity, electromagnetism, the strong and weak nuclear forces, and weave them into a unified theory that may eventually describe everything in the universe. Unlike classical physics, which treated forces and particles as separate entities, string theory suggests a profound interconnectedness between all aspects of the cosmos. Understanding the interactions of strings. Before we dive into how forces manifest from string interactions, it's crucial to grasp the core dynamics of how strings interact at a fundamental level. Imagine strings not as isolated, fixed entities, but as objects that are continuously moving, vibrating, and interacting with one another in higher dimensional spaces. These interactions happen when strings approach one another, combining, splitting, or even exchanging energy. The first kind of interaction we explore is fusion, where two strings come together and merge into a new single string. This fusion can create a new particle that has different properties from the original strings, potentially leading to an entirely new force or particle type. This new particle's behavior is governed by the combination of the vibrational states of the two merging strings, effectively altering the characteristics of the forces or particles involved. On the other hand, splitting happens when a single string breaks apart, each fragment becoming a new string vibrating in its own unique mode. These new fragments could lead to the formation of new particles, potentially affecting existing forces or even creating entirely new interactions. Just as particles can emerge from the fusion or splitting of strings, the fundamental forces themselves arise as mediators of these interactions. These basic interactions, fusion and splitting, are vital components of how we understand the universe's most fundamental forces. String theory allows us to visualize these processes and understand how they relate to the particle-like entities we observe in nature. Mediating the forces, how strings influence the fundamental interactions. With a fundamental understanding of string interactions in place, we can now explore how these interactions give rise to the forces of nature that govern everything from subatomic particles to vast cosmic structures. In string theory, each force, whether gravitational, electromagnetic, or nuclear, is understood as the vibration of a specific kind of string. However, this relationship is not a simple one-to-one mapping. Instead, forces are mediated through specific patterns of string vibrations that transmit energy, momentum, and information across space. Understanding these dynamics allows us to work toward unifying the diverse forces into a single framework. Gravity, for instance, remains the most elusive of the fundamental forces to explain within the realm of quantum mechanics. In classical general relativity, gravity is described as the curvature of space-time caused by mass. String theory, however, provides a quantum description of gravity through the graviton, a massless particle whose vibration corresponds to the force of gravity. In this way, gravity emerges as a result of string interactions, manifesting as an exchange of gravitons between massive objects. Electromagnetism, which governs the behavior of charged particles, is represented in string theory through the photon. The photon corresponds to a particular vibration of a string, much like how a plucked string produces sound waves. This specific string vibration mediates electromagnetic interactions, enabling the exchange of energy between charged particles. The unification of forces within string theory is particularly compelling because it provides a framework that describes not only the particles we observe, but also the fundamental forces that dictate their interactions. The strong nuclear force, responsible for binding atomic nuclei together, is mediated by gluons in particle physics. These gluons also arise from specific vibrational patterns of strings. Similarly, the weak nuclear force which governs radioactive decay is mediated by W and Z bosons, which are likewise described by string interactions. All of these forces emerge from the same fundamental framework, originating from the vibrational modes of strings in higher dimensional spaces. The role of higher dimensions in string interactions. One of the most compelling aspects of string theory is its insistence on higher dimensions, dimensions that extend beyond the three familiar ones of space and the one of time. While our everyday experiences are limited to these four dimensions, string theory suggests the existence of additional spatial dimensions hidden from our direct perception, potentially numbering 9 or even 10 extra dimensions. These additional dimensions play a crucial role in shaping how strings vibrate and, consequently, how fundamental forces manifest. In string theory, these extra dimensions are typically compactified, meaning they are curled up into incredibly small spaces that remain imperceptible to us. The specific shapes and properties of these compactified dimensions influence the nature of string interactions, ultimately determining the characteristics of the particles and forces that emerge in our observable universe. For instance, the way strings interact with these compactified dimensions could provide an explanation for why the electromagnetic force is vastly stronger than gravity, or why certain particles possess the specific masses they do. The geometry of these higher dimensions establishes the conditions under which forces interact, potentially dictating the fundamental interactions we observe within our four-dimensional reality. The unification of forces toward a theory of everything. One of the most profound implications of string theory is its potential to unify the four fundamental forces into a single framework, a theory of everything, TOE. The vision behind a TOE is to explain all of the forces and particles that exist in the universe using one consistent set of principles. For centuries, physicists have sought such a unification, but it was only with the advent of string theory that such a goal seemed within reach. String theory's ability to unify forces stems from the fact that all the forces we observe, gravity, electromagnetism, and the nuclear forces, are different expressions of the same fundamental concept, the vibration of one-dimensional strings. Rather than describing the forces as separate entities with their own distinct properties, string theory suggests that they are simply different manifestations of a deeper, underlying reality. The journey toward a unified theory is still ongoing, but string theory has already provided valuable insights. It suggests that gravity, for instance, is not fundamentally different from the other forces, but is simply another force that arises from the same dynamics of string interactions. The implications of this are profound because they suggest that, at the most fundamental level, the universe operates under a singular set of principles. Challenges and the path forward. While string theory offers a tantalizing glimpse of a unified theory, it also faces significant challenges. One of the main issues is the difficulty in testing the predictions of string theory. The energy scales at which string interactions would become apparent are far beyond what we can currently probe with existing experimental technologies. This has led some critics to question whether string theory is a testable scientific theory at all, or whether it falls more into the realm of abstract mathematics. Despite these challenges, string theory continues to inspire a rich body of research, and its potential to uncover the fundamental workings of the universe remains an exciting prospect. Researchers are actively exploring ways to test string theory, including by looking for signatures of extra dimensions or seeking evidence for the presence of gravitons. In the future, advances in technology may allow us to probe these higher dimensional spaces more directly, offering experimental validation for some of the ideas put forward by string theory.